I'm Roop Mahajan, Director of Institute for Critical Technology and Applied Science. I also hold shared appointments in the departments of Mechanical Engineering and Biomedical Engineering and Mechanics. It is my singular pleasure to welcome you all to the Hugh and Ethel Kelly Lecture by our distinguished speaker, the Nobel laureate, Dr. Eric Betzig. When we created this lecture series, we wanted to establish a forum for bringing scholars from all over the globe to share their thoughts and insights with the Virginia Tech community, and in that way recognize and honor the achievements of Hugh Kelly. Hugh Kelly earned his Bachelor of Science in Electrical Engineering at Virginia Tech in 1937 and a master's degree in 1938. Like our speaker today, he worked at AT&T's Bell Laboratories, where he played important roles in groundbreaking projects, including the 1962 launch of the Telstar communication satellite, the first private venture in space. Ethel Kelly generously supported Virginia Tech's College of Engineering and ICTAS as a way to honor her husband's legacy, and it is our privilege to carry on their commitment to advancing science and technology. Our heartfelt thanks to them for their generosity. Now I would like to say a few words about Dr. Sands, who will be introducing our keynote speaker. Tim Sands is the 16th president of Virginia Tech. He joined the university in June of 2014. He's a scientist, educator, and inventor, and has dedicated much of his life to advancing the impact of research and innovation in public education. He holds a bachelor's degree in engineering physics and a master's degree and doctorate in material science from the University of California, Berkeley. He's married to Dr. Laura Sands, a professor of gerontology in the Department of Human Development at Virginia Tech. Among the students and some faculty and staff, he's affectionately referred to as, by his Twitter handle, VT Sandsman. Before I hand over the podium to Dr. Sands, a few housekeeping items. Please turn off your cell phones, no photography, and please do not take any videos of Dr. Betzig's lecture. The whole talk will be available on the ICTAS website, www.ictas.vt.edu. And now, ladies and gentlemen, please join me in welcoming Virginia Tech President Dr. Sands.
Thank you. Good morning, and thanks very much, Roop. There are many ways to look at the world. You could look at the past by observing distant images in space, or you can look at rock strata. We could look to the future by doing predictive analytics and using big data. But they all have one thing in common: the constant push to see farther and better, or in the case of our speaker today, to see smaller. Eric Betzig earned his bachelor's degree in physics at Caltech and his doctorate in applied and engineering physics at Cornell. It was there his research involved near-field optical microscopy. His research venues, if you've heard, have included Bell Labs, the Ann Arbor Machine Company, and a boat on Michigan's Hillen Lake. On that boat, he says he worked with nothing but a laptop and a couple of really good ideas. His work is currently based at Howard Hughes Medical Institute's Genelia Research Lab, or Research Campus in Ashburn, Virginia. In 2014, Dr. Betzig, along with Stefan Hell, William Murner, received the Nobel Prize in Chemistry for the development of super-resolved fluorescence microscopy. According to the Academy, the ability to view biological samples at the nano level is now being used across the world to discover new knowledge that benefits mankind on a daily basis. Please welcome physicist, inventor, and engineer, Dr. Eric Betzig.
Well, thank you, Dr. Sands, for the introduction, and thanks to Roop, too, for his hospitality and hosting me here during this visit, and thank you all for coming. So I got the Nobel Prize for something called super resolved fluorescence microscopy. So what the heck is that? So if this thing here represents the size of a single protein molecule inside of a cell, then this big fuzzy blob that you see here is what it would look like in a normal optical microscope. Now, that's a problem because, in my opinion, one of the most significant questions facing science is how do we go from inanimate molecules like that protein molecule that are just a couple nanometers big and have them in some magical way self-assemble to create a bag that's tens of microns big that we call a cell that can move, can eat, can excrete, can reproduce, and is robust under perturbation. So it takes a licking and keep on ticking, even though what's happening inside is happening by chance at some level at the molecular level. So how does that happen? In order to know that, we need to be able to look at the living cell down to the very molecules that it's made of. Now, that's a problem because we have had for 50 years great imaging tools like the electron microscope, but they're really not good tools to identify particular proteins in the cell or to see those proteins in the living cell. And so that's what super resolution fluorescence is all about. So I was captivated by that problem going back to 1982 when I first entered graduate school and met my eventual thesis advisors, Mike Isaacson and Aaron Lewis. So Mike was an electron microscopist who one day turned his microscope around and used the electron beam to drill small holes down to a 30 nanometers wide inside of a thin film. They could then coat that film with an opaque metal. And then one day he and Aaron, who was a Raman spectroscopist, realized that if they could take that film with that small hole and place it very close to a specimen, then they would illuminate only a sub-wavelength sized part of the sample underneath. So it would act like a little nano flashlight that would, say, make a 50 nanometer wide spot. You could drive that around point by point and then get your super resolution image. So that was the idea that today is known as near field microscopy. So when I was a young graduate student, you know, I probably always read too much science fiction as a kid because I always wanted to do the big thing, some kind of a technical deus ex machina that comes out of nowhere and saves the day at the last minute or something. And most other projects seemed very incremental to me, but this seemed like potentially a breakthrough, even if risky. And although everybody else said it was a stupid idea and never would work, I didn't see it that way, and I said, okay, I want to work on this. And so I worked on that for my thesis, and after 6 years, I had the microscope you see at top there, which was a real ridiculous thing in retrospect. It ran off of 2 IBM PCs, and we were able to poke, as you can see it upper right there, a little bit beyond the diffraction limit with this microscope. Today, I kind of cringe at how crude those results were, but they were a step in the right direction, and it was enough to get me a job with my own lab at Bell Labs right out of graduate school. And so for the first couple of years, I actually struggled a lot and didn't really have any significant improvements in the technology. And I remember telling my boss after my second year review that if I don't have a breakthrough in the third year, you won't have to fire me because I'll quit. But fortunately, we came up with those breakthroughs in the third year, and a lot of it was from, instead of having those screens, going to pulled optical fibers that we would coat with metal, and that would efficiently deliver the light to the tip, as you can see it upper right there, and make that little nano flashlight now in a pointy structure that could then cover a rough surface much better than a flat screen. And with that, we got results like you see at the bottom there, where the middle image is the diffraction limited image from before, and the one at the right is what we could see by near field. So we were able to go way beyond the diffraction limit with this technique. Another technical innovation we developed was the light spreads very rapidly outside of that hole, so you have to be able to keep that aperture very close to the specimen. So what we developed is a means where we would wiggle the tip sideways by a few nanometers, and as it came close to the sample, there would be a slowing down of that wiggle because of the dissipative forces of the sample. You could measure that and use that to follow the topography of the sample as you're going along, keep the aperture at a constant distance. So with those innovations, the near-field technique finally took off. At one time, we did super-resolution photolithography, like you use to create integrated circuits. We looked at histological sections, like you would get from a pathologist beyond the diffraction limit. We studied at lower left here phase transitions in multi-component phospholipid monolayers. And the application that really, I think, put me on the map with near field was in '92. We used it to actually write bits of data in optical storage media that were at top much smaller than the bits you would see in that cross at the diffraction limit there. And so at that time, we had the world record of data storage density. And so this was something that garnered, a lot of media attention and so forth. And there were all sorts of efforts to try to get me to start sort of an internal big group to capitalize on this within Bell. But I really didn't want to do it because I've never had really the itch to lead a big effort or to do a big project like that. And really the reason that I wanted to do what I did with Mike and Aaron was because the goal was to make an optical microscope that would allow us to look at living cells with the resolution of an electron microscope. And that was still really the thing that was driving me, more so than the other applications of near field. So I said, just please leave me alone and let me work alone on other applications in near field. And the following year, we were able to do our first imaging of cells. These are now dead and fixed cells. But in this case, we're able to look by fluorescence, to look at, in fluorescence, you label your sample, your proteins of interest with molecules that glow under laser light, and then you look at that. And so you can get any particular protein inside of the cell to light up. In this case, that protein is a protein called actin, which forms the cytoskeleton that you see at right in the super-resolution near-field image versus the diffraction-limited image you see at left. So this was an important step on the goal, but it's still a dead cell. It led us in an interesting direction, though, because by just doing a calculation of the number of the amount of light we were getting out of our hole from just even a single actin filament, and knowing how many molecules there are on a single actin filament, it suggested that we might be able to see single fluorescent molecules. So this was a hot topic at the time because a few years before, my co-laureate W.E. Morner was the first to see single molecules by their spectral signature when imaging them at near absolute zero. And so there was many people who were trying to see if you could see single molecules at room temperature because this would be a big thing for biology. It turned out with the near-field technique, it was actually very easy to see single molecules because the issue isn't so much how much light a molecule gives up, it's how much background light there is from everything else that can glow inside of the volume. But if you shrink the volume down with that little near-field aperture, the background goes way, way down, and then it becomes easy to see single molecules. And in fact, in the upper left, what you're seeing are 3 different fields of the same molecules under different polarizations of the light. And what we realized is that rather than seeing round blobs like I showed you before, you see weird arcs and so forth. And that's because what you're seeing is the interaction of the orientation of the molecule with the electric field in that aperture. And once you know that, you can actually determine not just the positions of the molecules, but also their orientations. And you can determine their positions down to about a 50th of the wavelength of light. So this was kind of a win on several different levels and became an influential paper for what would happen later in my career. The following year in '94, I teamed up with my best friend at Bell Labs, Harold Hess. So Harold was working on another hot topic at the time called scanning tunneling microscopy, which could, on semiconductor and conducting structures, get down to atomic resolution and see the atoms. But he was using it to actually study superconductors. And so his STM ran at near absolute zero. And one day we took his STM tip out and put in my near-field probe to basically look at the light emission from semiconductor structures, in particular what's known as a quantum well that you see at bottom left, which is multiple sandwiches of different semiconductor material, which with electrical excitation can then glow and produce light, and particularly the kind of light that you have in a laser pointer, which I used to have on this table, but it seems to have gone missing. Where is it, Roop? Okay, oh, there it is down here. I got it, good. Now I can be more. And so now you have the spectrum that comes out from one point, and what happens is when you normally look at this in a normal optical microscope at absolute zero, you get a spectrum that's very squishy. But when you look with the near field tip, you see all of these really sharp lines, and if you move the tip even 100 nanometers away, the lines change completely. And what we came to realize was that the light emission inside of this quantum well sandwich couldn't occur anywhere, but what would happen is these excited states called excitons would move around and then get trapped in little potholes due to the roughness in that sandwich layer. And there they would collapse and give off light with the color of the light depending on the width of the pothole at that particular location. And so what was interesting, though, for later on was the idea and the realization that even though we had a small near-field tip, these things were really dense, and there might be a dozen or more underneath the probe at any one time. And so these sites were not resolvable in a conventional sense, but they were resolvable because they glowed in such pure different colors near absolute zero that if instead of looking at them in a space of X and Y where they overlapped, if we looked at them in X, Y, and color in a third dimension, then we could look at them individually and study the energy levels and so forth of these recombination centers. So by this time I had been doing near-field microscopy for a dozen years, from 82 to 94, and I was thoroughly sick of the whole damn thing. And part of the reason for that is the fundamental issues that I'll get to in a minute, but a lot of it is the sociological issues of technology development, okay? So I've been involved in the development of about 6 or 7 different technologies in my career, and they all follow this same trajectory. And when you're on the topic of developing it, you invest everything, and you put so much of your heart and soul into it. You love each one of those technologies as if they were your own baby. But just like your own baby, when it's born, you hope that it's going to cure cancer or become president, but in the end, you're just happy if it stays out of jail, okay? And so that's pretty much the way it is with technologies, too. And so I always like to get into this point where nobody believes in it, and I have the whole field to myself, and there's nobody banging my elbows. And then, you know, it's hard at the beginning. You know, you don't know, you're finding your way, and then eventually you start to get a little sniff that you might be on the right track because you keep trying things and iterating and failing, and few things work, and you start to kind of feel yourself falling into some potential well of understanding, and then eventually you get excited, you start to do some initial applications as with near field, and guess what? Then everybody takes notice. And then all of a sudden, instead of being alone, everybody's jumping into the field, right? And it gets very crowded. And those people, a lot of them aren't experts in that area. In fact, the vast majority are not experts. And so, you know, they start, because of the nature of academia and the nature of having to get grant money and so forth, is they start claiming crazy things. And so the whole thing starts to shoot off into this fantasy. You know, people were saying near field's going to cure cancer and do this and do that, and doing things that I know are just absolutely impossible with that technology. And so it made me incredibly frustrated. And, you know, my hope initially was that we would end up somewhere here. But once I realized what the real physical limitations, you know, I knew this was the reality. So the goal with any new technology is not any of this, it's how to make this asymptote as high above zero as possible. But it's kind of hard to see that in advance. But the whole thing got me so frustrated because I felt like by 94, with all the successes we had, there were hundreds of people starting to do near field. And I felt like every good paper we published was doing nothing more than providing the justification for 100 pieces of garbage that followed in its wake, and that every good paper and that, you know, basically everything I had done up to those 12 years was nothing but a net negative to society and a waste of the taxpayers' time and money. And so I was incredibly, disillusioned with the whole process, and particularly the whole academic thing. And part of my frustration was because I should have realized earlier the limitations of the technology. And the primary limitation is the light that comes out of that hole spreads ridiculously rapidly. And so if you're even 25 nanometers away, which is a very small distance, you're already losing significant resolution. Now, a cell is a heck of a lot rougher than 25 nanometers. So it was pretty clear that this was not going to be the path to allow me to look at living cells with the resolution of an electron microscope. And I was disillusioned and frustrated by that. I felt like I basically exhausted every good system one could study by near field, because I found every interesting system that was sufficiently flat and sufficiently close to the surface that you could actually apply the technology. But there was one other thing that kind of broke the camel's back. So, when I went to Bell in '94 or in '88, and my friend Harold went in '86, we became best friends almost immediately. And so Harold thinks a lot like I, and we both have pretty big egos, but we're both pretty shy. And when you go to Bell, when we did, there was 50 years of history behind it. Things like Telstar, like Kelly did, or the laser and the transistor, and you feel like you don't deserve to breathe the same air as the rest of the people in the building, And so how do you get rid of that insecurity? You work your butt off. And so Harold and I took pride in working harder than anybody. And so we would always race to be the first person in spot number 1 in the parking lot in Murray Hill. And we would each come in at about 4:30 in the morning, and if he had beaten me, I would put my hand on the hood of the car to find out by temperature how many minutes he had beaten me by. And so then we would work until about 7, and then we would go off and play tennis, come back at 8, work until 6, go to eat at the same Chinese restaurant down the street every night, come back, work until about 10 or 11, go to our respective apartments, collapse, and come back at 4:30, and do that 7 days a week. And so that's the kind of investment we put in our stuff. And after 6 years of that kind of thing, it turned us from those young and innocent guys there to those stressed and worn out guys that you see there. So couple that with my disillusionment with the sociology of academia and the limitations of the technology, and just sheer exhaustion. All of that was enough to make me quit. So in '94, I just suddenly quit, and that was that. And I didn't really have a plan B, but one day while I was trying to just push my daughter around in the stroller, I was basically a house husband then, it occurred to me that I could combine the single molecule experiment I had done with the quantum well experiment that Harold and I had done to come up with a different way of beating the diffraction limit. So the idea is that, remember in the beginning of the talk, in a biological sample, your fluorescent molecules are so close together that the fuzzy spots overlap, and you can't do a lot with that. But let's say that the glowing spots were different from one another in some way. For example, as in that quantum well experiment, say they all glowed in different colors. Then we could isolate them in a higher dimensional space based on their color or polarization or whatever. But once they were isolated, we could fit the expected fuzzy ball to the predicted fuzzy ball, and you can therefore determine the center position of the fuzzy ball to much better precision than the diameter of the fuzzy ball, and therefore know the coordinates of the molecule. If you did that with every molecule in the sample, you have a molecular resolution image of your sample, and you're doing it, without necessarily near field. You could do this in a regular microscope. So that was the idea, but there was clearly a catch, and I knew it even then, which is in a normal biological sample, there might be thousands of molecules in one tight focus of your microscope. And so whatever you use to see these, you need to see them one at a time to find their centers. And so you would need to be able to have exquisite resolution in that third axis to be able to see one molecule on top of hundreds or thousands of others. And there was no really good way to do that at the time. And plus, I was unemployed and had no lab to do this type of thing, so I just basically threw the paper out into the literature and left it at that. Because of those limitations, I almost didn't publish that paper, but in retrospect, it's a good thing I did, because it was one of the 2 papers the Nobel Committee cited for giving me the prize eventually. So in the end, I took a radical turn and said I didn't want to do academic science. So in the mid-'80s, my dad had started a machine tool company that by the mid-'90s was very successful. And they would make these large machines, you know, a human is like this on this scale, that would be custom designed specifically to make one part, this, or this, for the auto industry. But it would make them 24/7 around the clock every 30 seconds for 1 million parts per year. And that's why you had to customize the machine to the part. And so I thought, you know, I had enough ego remaining from my near-field days and enough naivety from not having been in industry that I felt like, well, if a good physicist goes to the Rust Belt, I can save them from the Japanese if I just put a little real science into this thing. Well, that's how stupid I was. So anyway. So I worked in my dad's business for 7 years, and my proudest accomplishment was this machine here. So it used, you know, in the 30s and 40s, most machine tools were driven by hydraulic cylinders. They were messy, they were slow, they were noisy, they were inaccurate, and certainly by the 90s, everybody had switched to electric drives. But hydraulics has major advantages, as anybody in aerospace will tell you, in terms of power to weight ratio. And so I was able to marry modern nonlinear control algorithms to energy storage principles in hydraulics like you have in a Toyota Prius or something, and be able to then use modern servo hydraulic technology to make a machine that would collapse something the width of this auditorium into something the size of a little Fiat. And so it would move 4 tons at 8 Gs of acceleration and position it to 5 micron precision, anywhere inside a meter cube volume, moving in 100 milliseconds. So it was much smaller, much cheaper, much faster, take much more productive, aggressive cuts on the specimen. And I spent 4 years developing it, 3 years trying to sell it. In the end, we sold 2 of them. And so it was an incredible disaster. And it was because I misread the market. I misread, you know, what goes into the decision-making process to buy these types of machines, and because I was really naive. It was technically great, but as a product, it was horrible. And so after burning through a couple $1,000,000 of my dad's money, I apologized to him and said, you know, Dad, I've done everything I can, but I just can't think of anything else that's going to make this thing sell. And then I quit again. And so that was 2002. So that was clearly the darkest time of my life, because not only had I thrown away an academic career, I'd also thrown away the backup possibility of following in my dad's footsteps. So now I'm 42 years old. I have 2 small kids. I'm unemployed, and because I burned my bridges really well, probably unemployable, okay? And so I did something smart, which is I hooked up again with my friend Harold. So as you may know, Bell sort of imploded through the 90s and continued to contract, and more people had to leave and spun off. Harold left in 96, landed working for a company that makes test equipment for disk drives. But when I hooked up with him again, we were kind of having similar thoughts in that, you know, while he still had a job, we were all both dissatisfied. We were both going through our midlife crisis at the same time. And so we started to meet. He was in San Diego, me in Michigan. We'd meet in various national parks and just start talking about, you know, what do we want to do? You know, is there a meaning to life at all? You know, what's the point? You know, this kind of thing, you know, all this kind of black thoughts or whatever. But what we sort of discovered is that, while neither one of us felt like we would be comfortable in a university environment, we both really miss doing science, and really miss doing science with our own hands. You know, in business, you know, you have to take some kind of administrative responsibilities to get anywhere. And so you get further and further divorced from the things that we love and the things we do best, which is to build things and to design experiments and take data. And we wanted to see if there was some way we could get back to the lab without the other constraints that would keep us from being in the lab. And so I started reading the scientific literature again for the first time in a decade. And one of the first papers that really struck me in the face was Marty Chalfe's paper about green fluorescent protein. So the idea that you could snip a little bit of DNA out of a glowing jellyfish and splice that in next to the DNA of any protein you want, and then get any living organism you want to produce that protein in a glowing form that you can then visualize in a microscope, was to me nothing less than magic. It was the most revelatory thing I had ever seen, because when I had done that actin experiment I showed you before with the near field technique, the microscope was certainly a problem, but getting the fluorescent molecules onto the actin in a dense enough way, in a specific enough way, was a huge challenge that really limited the whole thing. But now the cell does it for you for free and does it inside of the living cell. And so when I decided I wanted to get back into science, I knew two things. I didn't want to do anything with machine tools, and I wanted nothing to do with microscopy. But when I read Chalfie's paper, I said, God damn it, I have to do microscopy again. So this is when, as Tim was saying, that was when I was in the cottage with the laptop for a couple of years, trying to think about, I need some intellectual capital because I haven't done any science for 10 years, and who the hell's going to listen to me? So I needed an idea. So I started thinking about ways of capitalizing on GFP by making a microscope that would create this massively multifocal excitation field to, in parallel, read out everything that's happening in 3D inside of the living cell at once. It used these things called optical lattices that were developed for trapping atoms near absolute zero. But I figured I came up with a theory for new classes of optical lattices that would be useful for microscopy. But now I needed to sell this idea. Well, the first person I tried to sell on that idea was my buddy Harold, because Harold is simply the finest scientist I've ever known and the finest experimentalist and engineer I've ever known, and also the most humble man I've ever known. And he liked the idea, but he didn't really want to do it with me because it was my idea, and he wanted his own idea. But he was certainly willing to help me try to sell my idea. So one of the places we went was Florida State, where they have the National High Magnetic Field Lab. And one of our old friends from Bell was the director of that now, and he had been trying to recruit Harold to come to there. So Harold, on an earlier visit, met this guy, Mike Davidson, who does live cell imaging there, and said I should talk to him. So we went together down there, and on that visit, we learned about a new type of fluorescent protein. So rather than in a normal fluorescent protein like Chalfie developed, if you shine blue light on it, it glows green. But with these photoactivated fluorescent proteins, if you shine blue light on it, nothing happens. But if you shine a little violet light on it first, you activate it, and then shining blue light on it makes it glow green. And so Harold and I were sitting in the airport in Tallahassee, and all of a sudden we both just sat there thunderstruck with our mouths hanging open, realizing that this was the missing link to make the idea that I had pitched in my first round of unemployment 10 years earlier to work. And so the idea is that if you turn on the molecules with the violet light at such a low intensity that only a few of them come on at a time, then those fuzzy blobs are separated enough that you can find their centers. You turn on another subset and another and another, and eventually you'll find the positions of all the molecules in the sample. If you sum the fuzzy balls, you get back to the regular diffraction limit, but if you plot the centers, you start to build this super resolution image. So it's the same idea I had in 1995, but now in 2005, that discriminating third axis is time, and we can get as much resolution as we want on that third axis by controlling the intensity of the violet light. So this excited us tremendously, and we immediately dropped the lattice idea, but it also scared us a lot because we were concerned that why hasn't anybody done this already? This is so ridiculously easy. Somebody's got to be doing this or have done it. And so we were terrified with every passing day that a paper was going to come out the next day and we would be scooped. And so we said, you know, that I had been able to convince Harold in my quest to try to get him to do the lattice to quit his job. So we were both unemployed. But it was like, you know, so how are we going to do this? It's going to take too long to get venture capital funding. A grant would take way too long. And so we said, well, screw it, let's just do it ourselves, okay? And so the good news is that when I left Bell, I pretty much told them to go to hell, but when Harold left Bell, he was able to take all of his equipment with him. So we pulled that out of the storage shed, and we put about $25,000 each of our own money into it. And normally you do that kind of entrepreneurial thing in some smelly, oily garage, but we were able to do it in his living room because he wasn't married, so there wasn't anybody to object to that, and it was more comfortable there. And so this is the first Palm microscope there, photoactivated localization microscopy. You know, I've done a lot of fun things in my career, and it's hard to choose, you know, what has been the most fun part of my life. Bell Labs was great. Working for my dad was great. Being at Genelia is great, but if I had to choose, I would say working with Harold over those 6 months in that living room was always going to be the pinnacle of my career. You know, we were both unemployed, but we were both on a mission. We were back to working just as hard as we did when we were at Bell, always trying to one-up one another in a friendly competition and put this thing together. We did have one major problem. We put the whole thing together in 2 months. But the next problem was we knew zero about biology, because you're talking to two condensed matter physicists here. So, but the good news is that I was also slated to give a talk about my lattice microscope to try to sell that idea to NIH. And so on that talk, I asked if Jennifer Lippincott-Schwartz and George Patterson could come to that talk, who were the inventors of this photoactivated green fluorescent protein. So they did come to the talk. And I invited them to lunch, and I swore them secrecy, and I told them the idea and said we needed their help, and Jennifer said, fantastic, bring it by. I didn't realize Jennifer says fantastic to everything and everybody, but we took that as a yes. And so we then shipped the microscope from San Diego to Bethesda, and then we started working with Jennifer and George. And very quickly, this is a cut through a cell, a very thin section through a cell. These are two lysosomes, which are protein-degrading objects, sort of garbage dumps inside of the cell. This is the diffraction-limited image. That's the super-resolution Palm image. And to better appreciate the resolution, you go from that to that. So with with the right type of sample and the stars aligning, and I'll talk about that later, you can immediately go to about 20 nanometer resolution, or 10 times beyond the diffraction limit with this, with a microscope that you can build in your living room. So needless to say, this quickly became a very big thing, and many, many groups jumped on. We just barely beat there were 3 other papers later that year with basically the same kind of concepts, but we were the first. So that was the other paper that got me the prize. So, you know, we went from the idea of Palm to having all of the paper and all the data in our science paper that got me the prize in 6 months. Okay, so that's how quickly you can move if you're motivated enough and also isolated enough to really have that total focus. So that's all the good news about Palm, and you know, the rest is history, as they say. But there's still many problems in super resolution in general. The first of them comes down to the fact that what you're looking at in a super resolution fluorescence image is fluorescent molecules. But they're not really the thing you care about. The thing you care about are the protein molecules to which these fluorescent molecules are attached. So they're just indirect reporters. Now, if the protein molecules are decorated on a structure like this, it's easy to tell what it is. But if they're decorated only this often, you can miss that structure completely. So you have to have a high enough density of fluorescent proteins in your sample. And if you do the back of the envelope math, it turns out to be numbers of fluorescent proteins which are considerably higher than biologists have been accustomed to creating in their samples up till that point. That doesn't mean that they can't get there, but it is a big challenge. And it means that the challenge of super resolution is all in the hands of the biologist as opposed to the instrumentation developers, which makes it very difficult. And the reality is that even this density is not enough, and you need almost an order of magnitude more to get around sort of the chance stochastic aspect of where the fluorophores land. So in the end, you can still ask, why do we care? Why do we care about super resolution fluorescence? Well, there's really two reasons. An EM image, an electron micrograph, is still, as good as the resolution is, it's looking at something dead, so you want to be able to do live, and it's looking at something that in the end is a black and white image. But there's 10,000 different types of proteins in a cell, and you want to know where everyone is because they're the things that drive cellular function. That's what fluorescence brings to the table. But that means you can either do structural imaging with fluorescence and protein-specific contrast, or you can do live imaging. If you do structural imaging, the most common way to sort of get everything stable to image is to put chemical fixatives to kill and fix the cell in place. So that's 95% of what we think we know from super resolution comes from chemically fixed cells. But the problem is the chemical fixatives change the very ultrastructure you're trying to image. So here you can see these actin filaments are dimmer and some are blown out by fixation. This is looking at the endoplasmic reticulum, a protein sorting machinery inside of the cell. This is in a live cell, then this is fixing it and showing you get all of this aggregation and like that. This is what you would throw in the microscope. If you're naive, you would think this is the real structure, but it's not. This is, okay? And so these are major problems in the field. And then the other fork in the road is you can say, okay, well, I don't need to fix the cell if I look at the cell live, and honest to goodness, isn't that really what we care about? That's why I got into this business back in '82, was to look at the live cell. But the problem is that the two methods that shared the prize have a lot of limitations for live imaging. The first is that if you do some back-of-the-envelope math, based on claims in the literature of resolution people have gotten, you required the cell to give up anywhere from thousands to tens of thousands of times as much light to create one image as in a diffraction-limited image. Now, a big problem with fluorescence is that the fluorophores don't last forever, but they bleach, they turn dark. And so it's very difficult to get anything to go even 100 times as much light as diffraction limited and not be totally dark by bleaching or totally dead from all the light you threw at it. The next problem is that these methods require orders of magnitude more intensity than light evolved under. So the two methods that shared the prize are something called STED, which was developed by Stefan Hell in Germany. In that technique, you excite the molecules in a spot, and then you turn off all of the molecules with another light beam, except those at the very center of this little donut of light to leave a little pool. That's great, but now you have a tiny little spot that you have to drive around point by point, just like in my old near-field technique. And because it's serial, it's slow. And so it takes a lot of time. And to make it fast, you need to put in a lot of light so you don't dwell very long at any one point. So you put in anywhere from tens of kilowatts to gigawatts per square centimeter, whereas light evolved at 1/10 of a watt per square centimeter. Single molecules, like we look in POM, require kilowatts per square centimeter. So all of these methods, you're wondering, what the hell are we doing to the cell when we claim we're doing live cell imaging, as opposed to looking at tortured, dying cells, okay? And so that's a major problem. So as a result, I mean, it's pretty obvious that there's going to be trade-offs. Any engineer, and this is an engineering school, you guys should know about trade-offs, right? I mean, you very rarely get something for nothing. And so if you want higher spatial resolution, you need to take, you need to have more pixels, and that means you're taking more measurements. That's going to take more time and means you're throwing more damaging light at the specimen. So you're always playing off spatial resolution versus damage to the cell versus speed versus how deep you can image. So by 2008, excuse me, I talk too much. So by 2008, I was exactly where I was emotionally when I was in '94 with the near field technique. I was, because, you know, super resolution by 2008, everybody's doing it. It was declared method of the year by Nature Methods. It's all in all the popular press everywhere. Everybody's saying it's going to do everything, okay? And I was just as disgusted by the whole thing as I was of near field in '94, and I wanted out. So I felt like I was living the same bad nightmare all over again. So I pretty much turned my back on super resolution for a number of years. As you'll see, I returned to it for various reasons. And because I was now a little older and hopefully wiser, I didn't immediately quit Genelia, which would have been a shame because it's too nice of an environment. But I needed to find other things. But super resolution came back to haunt me 6 years later when I was given the Nobel Prize for it. So look, it's nice to win the Nobel Prize, and I'm grateful to win the Nobel Prize. But I also feel, A, that super resolution was really premature to win this award because it's still sorting itself out as a field, and the applications, although there, are really not, I think, Nobel worthy at this point, and we still have to wait for things to develop. But I also feel like a tremendous hypocrite for accepting the Nobel because I've always felt like prizes are incredibly toxic to science. And if I were king of the world, I would do away with all sorts of prizes and awards in science because, you know, what matters are the actual accomplishments. The things I'm going to remember are when Harold and I first saw a field of molecules pop on in the microscope, or, you know, seeing my near-field microscope work for the first time, or any other technology I've worked on finally coming to fruition. Those are the real awards. And, you know, things like the Nobel, it's just subjective. It's the opinion of 6 people sitting in a room. And, you know, they're not the experts. They get advice from a bunch of experts, but they're not. And so, you know, it arbitrarily creates winners and losers. And I've been on the outside of awards too, and I can tell you the pain of being on the outside is far worse than the pleasure of being on the inside. And overall, it just is just a, if you're working for awards in science, you ought to find another occupation because you're motivated by the wrong thing. Okay, enough said. All right. So so again, I was faced with this problem of I wanted to do live cell imaging. That's why I got into this business in the first place, and I didn't have the right tool to do it. The tools for super resolution. Localization does have some niches in live cell imaging. I'm not going to go into those today. But there's actually a third method of super resolution that is much better for live imaging called structured illumination microscopy. So in this method, instead of illuminating your cell uniformly, you put a grading of illumination on it. And then by doing that, you're able to get information that's up to twice beyond the diffraction limit and still be able to see it. So that gets you to 100 nanometer resolution. That hard limit of 100 nanometers was the reason why the Nobel Committee said that it doesn't deserve to be part of the prize. But in my opinion, the 100 nanometer resolution of SIM is in some ways its strength. Because first, you don't need the insane labeling densities that the other methods need that are hard to get at. Second, it takes far fewer raw images to distill into one super resolution image. So it's far faster and more compatible with the speeds that actually exist in live cells. And third is it requires far less light thrown at the cell than the other methods, so it's far less invasive. So the guy who understood these trade-offs sooner than all of us was Mats Gustafsson, who developed this technique around late 90s, early 2000s as a postdoc at UCSF, and then we recruited him to Genelia in 2008. So here's exploring two of the huge advantages of structured illumination for live imaging. So this is the endoplasmic reticulum, like I said before, sort of this protein sorting machinery in the cell. So the resolution is only 100 nanometers, but look at what we're seeing. We're seeing all of this dynamics, and it's beautiful. And you're seeing it here for 1,800 time points. That's 2 orders of magnitude more than any other super resolution technique can look at a live cell. Here you're looking at that dynamics of the endoplasmic reticulum at 50 frames a second, which is 1 to 2 orders of magnitude faster than any other super resolution method. So it's blazingly fast, very non-invasive, only 100 nanometers, but there's a wealth of information at that level that you get. You learn that the cell is complex, that the cell is beautiful, and the cell is very dynamic, and you need tools to be able to explore that. So all of that's great. The bad news is that Mats was diagnosed with a glioblastoma in 2009 and passed away in 2011. So I basically inherited his group and his people, and so I consider Mats the Messiah of the gospel of SIM, and I'm his acolyte, and I spread his message everywhere I go. So if one of the reasons the Nobel Committee said that it doesn't deserve to be part of the prize is that limit of 100 nanometers, how can we improve upon that limit? The simple thing, if you're an optical engineer like myself, is just find an objective that has the tiniest diffraction limit possible by having the highest numerical aperture possible. If you work in a mode where you just illuminate the bottom of the cell in what's called turf, you can go up to a very high numerical aperture that gets the resolution down to 84 nanometers, which is pretty good. And with that, we can study the flow of proteins in these contact points, sort of the feet of the cell, and how the cell attaches to a substrate. You can look at the proteins which create the sort of forces that squeeze the cell to push it along as it migrates on a sample. And so if we want even higher resolution, though, then we need to resort to the sort of switching tricks, like the turning on the molecules that Palm used, and the similar switching tricks that the STED approach uses. So by using a photo-switchable fluorescent protein that can reversibly turn on and off, we can use one standing wave to turn on a subset of molecules, another standing wave to excite these molecules, and because we put on 2 gratings instead of 1, we're able to extend the resolution to 3 times beyond the diffraction limit instead of twice. So that takes us to 62 nanometers, but we're able to still do it in a way that we can then look at live cells at 62 nanometer resolution for up to 30 frames and then follow dynamics. In this case, is that actin cytoskeleton where I started back in '93, but now looking at it live. So in my opinion, it wasn't until this result in 2015 that I finally achieved the goal I set for myself when I entered in grad school in 1982 to be able to look at the dynamics of the living cell non-invasively with the resolution comparable to an electron microscope. And so finally that goal was reached, but it happened in a very circuitous way. And so we had a paper last summer talking about all the different applications of this for looking at different structures, from endocytosis, how cargoes get inside of the cell, to how those cargoes evolve in the endocytic pathway to bring things into other parts of the cell, to how actin fibers are created out of individual actin filaments by other proteins, and so on. And so the moral of the story of SIM is that while everybody else in the super resolution field was marching as fast as they could up to this apex here and thinking just single-mindedly about resolution, Motz understood that there's a lot more to a microscope for a biologist that matters than just simply spatial resolution. And so by marching back in this other direction, he had a whole playground all to himself and a much larger application space in which to play. And so in 2008, when I grew frustrated with Palm and super resolution in general, I asked myself, can I learn from that? Is there something I can do to then perhaps go even farther? What if I go to the diffraction limit? Is there something I can do as a physicist to make a microscope that would allow us to look at the dynamics of living cells in 3D that would be as transformative in terms of the gains in speed and resolution, or speed and non-invasiveness, as Palm was in terms of spatial resolution? And so why is that important? Well, the hallmark of life is that it's animate, and every living thing is a thermodynamic pocket through which matter and energy is flowing continuously. So while structural information that you'll get from an electron microscope or a fixed cell super resolution image is always going to be informative, by far, the only way we're going to be able to understand that basic question I posed in the beginning of how inanimate molecules come together to create the animate cell is going to be by imaging across all 4 dimensions of space and time with high resolution at the same time. So the good news is that the standard tools that biologists use to do 3D live imaging leave a lot of room for improvement. They're basically the wide field microscope, like you've probably all used in a high school biology class, and then the confocal microscope, which uses a focused spot of light, which is then the light goes back and collected through a little pinhole to strip out the out of focus component. So those techniques work, but they're very inefficient because they illuminate the entire thickness of the specimen, even though only one plane, the focal plane, is in focus at any given time. And so they create a lot of unnecessary bleaching and toxicity of the regions above and below. So in my opinion, one of the most important innovations in microscopy of this century has been when Ernst Stelzer at the European Molecular Biology Lab reintroduced a 100-year-old idea called plane illumination. So in that, instead of illuminating from above and then collecting the light back, you bring a second lens from the side, in this case a cylindrical lens, to create a sheet of light which then illuminates only the region around the focal plane. So you get no bleaching and toxicity of the regions above and below. You get no out of focus haze in the image. And you can use a fast camera to snap that because it's all illuminated at once, then move that plane up through the specimen and get your 3D image. This has been transformative for studying embryogenesis at single cell resolution. But it has one limitation, which is that if I want to study subcellular detail inside of single cells, there's a trade-off between how flat a light sheet is and how thick it is. And over the dimensions of a cell, it's about as thick as the cell, so you don't gain much benefit. So that's this here. So I asked myself, is there a way of decoupling how thin the light sheet is from how flat it is over how long it is? And there is, and it's a physics trick called a Betzig beam. So in the normal light sheet microscopes, you illuminate with a spot of light, you make a spear of light out of the objective that's thick and long. Long is good, thick is not. But if you illuminate instead with a ring of light, you can basically have two knobs, the diameter of the ring and the thickness of the ring, to control independently the length of the pencil and the thickness of the pencil. So you can make a much smaller little pencil of light, which you can sweep then to get a much narrower sheet of light through your specimen. So the pencil would scan in and out of the screen, and we go up by up plane through the specimen. So if you do that, then you're able to create images like this. So this is looking at a cell which has been transfected with a cancer signaling protein, which causes it to create all of these ruffles that fold over and encapsulate fluid in these little vacuoles or bubbles that you see in this sort of X-ray view of this data. So this data is, at least an order of magnitude faster and longer in its imaging, and it's a factor of 3 better in its axial resolution than the best live cell microscope prior to that. And so, so this was a major advance. Now, one thing we had to do in order to get this speed was, instead of having a single Betzig beam, is we used a diffractive element to create an array of 7 parallel Betzig beams. And well, that solved the speed problem, but what was shocking was how much less toxic it was to run with 7 beams instead of 1. And what I've learned now in doing 8 years of live cell imaging is, while the total dose of light you throw on the specimen is an important metric of its health, a far more important metric is the instantaneous power delivered to the cell. So seen in this light, the confocal microscope, which has been the gold standard for biologists for live cell imaging, is probably absolutely the stupidest possible way to do live cell imaging. Because not only do you have these cones of light that deliver the light to the focus and doing all this unnecessary bleaching and toxicity, at the focus itself you have an actinic spot of light that's going, and it leaves death and destruction in its wake as it goes. And so the moral of the story is, a line is better than a point, and a plane is better than a line. So why would you stop at 7 beams? So I started to model what would happen if the Betzig beams started to come so close together that they started to interfere with one another by, optical interference. And what you find is you go through these resonances of destructive and destructive interference, but there are certain magic periods of the pattern where you get 3 wonderful things to happen. First, you get near destructive interference to get rid of side lobes that exist around the Betzig beam that create some out of focus excitation and loss of resolution that you don't want. Second, you have near 100% on-off contrast, a grading in the plane of the sample, which is ideal for doing super resolution by structured illumination. And third, you spread the energy out to be the absolute minimum it can be in terms of peak intensity across the cell. And so it's a triple win. I am an engineer, okay? Engineers always think in terms of trade-offs. When you can win 3 times and lose none, that's like a unicorn. And so you feed it carrots and you take it home, okay? I mean, it's a big deal. And so that's become what we now call the lattice light sheet microscope. The reason we call it that is, and the reason why, while I was excited about this result initially, I was also extremely angry at myself, because these magic periods where this happens are nothing more than the magic periods that I predicted in this theory of optical lattices I developed while I was in that cottage and on my motorboat with my laptop, and threw it all away in order to do Palm. And once I realized that connection, I could take that stuff out of the trash can and then use it then and figure out how to apply it to lattice light sheet microscopy. So this is showing the concept. You have an optical lattice creating a 2D lattice light sheet there. You dither it back and forth a little bit in order to make a sort of uniform sheet. The cell sweeps through that. You get fluorescence in orange like that, and you just zip your way through the cell. So here's some applications of that. This is looking at much of what we know about cancer, about cell motility, is by looking at cells on cover slips. That's a pretty bad model of metastasis, so you need to look at motility in 3D. So here you're looking at a neutrophilic cell and how he actually moves through a collagen mesh. Here you're looking at T cells like would fight infection in your body. One of the steps in the process of finding out if it's the right T cell that should replicate is in the lymph nodes. You'll have dendritic cells which have these complexes that say what the infection is come, and the T cell has to latch on and find out if he's the right T cell for the job. And so this is showing the process of creating what's known as the immunological synapse. And we identified this previously unknown extremely fast actin flow along the sides of these T cells as they establish that synapse. Here we're looking at a slime mold amoeboid, which is very light sensitive, and in a few frames in a normal microscope he'll just round up and go, ugh. But here we can look at him for hundreds of points, and you'll see as the movie comes around, you see that little lightning bolt there? So our collaborators see that and they say, what the hell was that? And we say, we don't know, you're the biologist, you tell us. So, you know, every time, every sample that we throw into this microscope is a new adventure. You know, I don't want to pat myself on the back, but I've never felt more like Galileo than with this microscope, because every group that comes by sees something new, because they just haven't had this combination of space and time resolution before. And it's fine to win the Nobel Prize for Palm, but I am morally convinced that this will be the high water mark of my career, this microscope, just based on the reception that the biological community has had, and how many novel findings are coming out all the time with this microscope. And so, so that was a big one. If you like these movies, we put together a little Vimeo album. You can just Google Lattice Light Sheet Vimeo, and it'll take you to like 40 movies like this if you want to see cells doing their little dance. So one of the things that lattice light sheet turned out to be really good for, in addition to looking at cellular dynamics, was one of the skeletons in the closet of the whole single molecule and super resolution field is that if the cell is more than a few microns thick, out of focus molecules create so much background it's impossible to see in focus molecules. So here we're looking at transcription factors necessary to get RNA generated inside of the nucleus. This is a whole bunch of cells, 35 micron spheroid cells. The out of focus stuff makes it impossible to see those transcription factors. But if we park the lattice light sheet at one plane, we have great signal to noise to see the single molecules, and can look at the binding kinetics of these transcription factors and then find out exactly where with super resolution transcription is happening in the nucleus. So this lattice light sheet then brought me back to high resolution, super resolution by single molecule localization again, because now we're able to get around. Remember I said the problem was getting labeling density, getting enough label in there. Well, in the same year that we published our Palm paper, another group published a related idea where instead of turning on the molecules with light, the molecules are around your cell in the media and whizzing around so fast under Brownian motion you don't see them. But when they stick to the cell, then they're a little glowing spot and you localize them. That's called paint. The advantage of this paint approach is that unlike Palm, where you load up the molecules at t equals 0 and then you have a finite budget to work with paint, because they're constantly coming out of solution, there's an infinite army of them that can keep coming, and so if you just wait long enough, you're going to get enough density of label. and then that gets around that problem. So now 3D localization microscopy looks like a 3D EM image, but now with protein or cellular contrast that you don't get in the EM. And furthermore, you can then apply it to very thick specimens. In this case, a dividing cell, these are the retraction fibers. You get these sort of little microvilli on top of the cell when it's in mitosis. That's a diffraction-limited image of the chromosomes by lattice light sheet. And now we can cut away and we can see the endoplasmic reticulum, which remember looked like a net before. That all folds up into these little pockets when the cell divides that you can see there at high resolution. We've even taken that to the point of looking at whole clusters of cells, like in an organ on a little fish that we study. So that takes us to the last challenge, and that fish again. So ultimately, what we want to be able to do is to be able to look inside of the living organism with high resolution. And there's a challenge with that in that because proteins have different refractive indices from cytosol, from lipids, from DNA, and all the rest, there's the light that goes in gets scrambled. So the lattice light sheet gets scrambled going in, and the light created by that light sheet is scrambled coming out. So it's basically like the water on your windshield before you turn on the wipers. That's still transparent, that water, but it warps and scatters the light in a way that you can't really see the cars in front of you. And that's the situation you face whenever you try to do optical microscopy more than one cell layer deep inside of an organism. And so, fortunately, this is a problem astronomers had to deal with 50 years ago because the atmosphere does the exact same thing to light from distant objects. And so they developed a technology called adaptive optics. So what they do is they shine a laser out of their telescope up into the stratosphere to excite fluorescence from some sodium atoms to create a bright artificial star that's next to the extremely dim object from 10 billion light years away they want to see. Both of those things, the light from both those objects then come back through the atmosphere, and they're both warped in exactly the same way because they take the same path back into your telescope. You strip out the light from the guide star, you put it in a computer, and you change the shape of a mirror to exactly balance the warping of the atmosphere by changing the shape of that mirror to go ding from there to there. So the best ground-based telescopes would never dream of not using adaptive optics now, because without adaptive optics, the seeing power is no better than a reflector you can have in your backyard. Okay, so it's huge in astronomy. So we use these same ideas of a guide star, in our case created by a 2-photon microscope, to go inside a transparent fish called a zebrafish. So at left you're seeing using 2-photon microscopy to image a subset of neurons in the brains of a zebrafish embryo. And so one of the challenges in microscopy AO we face is that as you move from place to place in the specimen, you need different adaptive corrections. So this is 20,000 corrections to cover this volume here, but we do it in 7 milliseconds. That's turning the adaptive optics off. That's what you would see with a state-of-the-art microscope today. This is turning the adaptive optics on. So basically it's not super resolution, but it gets us back to the diffraction limit. Here what you're seeing is what happens looking at the soma of a neuron buried deep. We can't see the mitochondria, the powerhouse organelle of the cell. Without adaptive optics, it's just a fuzz, but with, you can see those mitochondria just as well as if that were a cell on a cover slip. And so that brings us to really the vision for my group going forward, is that I was trained as a physicist, and physicists learn on their mother's knee about Heisenberg and the idea that if you make a measurement of a system, you're going to perturb that system, right? Well, I believe that we have never actually studied the natural physiology of the cell for 3 reasons. First is that our most dominant tool to understand proteins inside of the cell has been fluorescent proteins. And usually we have little control over how much protein is generated, excess protein with a fluorescent handle. And so you change the homeostatic balance of the cell. So in the last few years, there have been these new genome editing tools that allow us now to finally make sure that we only produce proteins at endogenous original levels, which would allow us then to take a big step forward. The next challenge is we've used tools to look at the live cell like the confocal microscope that, as I said, is far too damaging and far too perturbative to the native physiology because of the light levels. That's where the lattice light sheet comes in. And then the third problem is that much of what we know about cell biology is by looking at cells on cover slips, and it's damn for sure they didn't evolve there. And so what we need is the ability then to take these tools in to look at the cells inside of their native environments and the organisms in which they evolved. To do that, we have to marry the lattice light sheet technology to the adaptive optic microscope technology, and then eventually spin in super resolution on top of that. So this is the beginning of that. This is a lattice light sheet microscope. This is an adaptive optical arm that corrects the light coming out. This is an adaptive optical arm that corrects for the light sheet going in, and then that's the lattice microscope itself. So about 4 months ago or so, my postdoc Sung Lee finally got this working. So you can see as we go through a membrane-labeled zebrafish, looking at all the membranes, these are muscle cells on the side. This is going to the notochord in the middle of the cell, or the middle of the embryo during mid-development. And you can see how when we turn the AO off and on, that the improvement. Now we build up a volume from that, and now we're going to cut away this volume. But now because, remember when I showed that zebrafish neurons before, that was 2-photon microscopy, so it was a point scanning method. To cover that volume took 18 hours to get that one volume. Now we're covering a volume only a little bit smaller, but we're doing it in 7.5 minutes instead of 18 hours because of the lattice. So now we can then, over a very large part of a developing organism, study at diffraction limited resolution, subcellular detail anywhere we want inside of that organism. So an example of that is this is some data from last week that I thought was really cool. This is looking in the ear of the developing zebrafish. This is a fluid-filled cavity inside of that ear. And what you're going to see is you can sometimes see these very fast zip of blood vessels, but now you're going to see this is a macrophage. So he's sort of the scavenger inside of the cell to, eat up bacteria or other debris. And so you can see how he, works his way around and so forth. We've seen macrophages on cover slips, but they're not, by the lattice, but they're nothing like this in terms of their dynamism and so forth, and the morphologies they create. And it really shows exactly how we're finally at the point where we can really get 4D high resolution inside of the whole organism, which is really, I think, the end goal for this type of microscopy development. So the last thing I want to say, and I know I've run pretty far over, but another thing that's very important to me as a technology developer is to see the technology be used. I mean, to me, publishing a paper is nothing. It's really just the beginning salvo in a process to try to get technologies in the hands where biologists can answer questions. No technology I develop means diddly squat if it doesn't answer biological questions in the end. I'm not a biologist, and so I'm not going to be answering those questions myself. It needs to get out there. So we take a multi-pronged approach to that. The first is to generate interest in the technology. So, we bring lots of people into our lab, but at some point, we have to say stop and then go on to develop the next tool once an existing tool reaches maturity. At that point, we've partnered with the Gordon Moore Foundation to create an advanced imaging center at Genelia, where we're able to toss our developed technologies to the imaging center. They have staff there that can run these, and then it's only for outside users. So anybody in the world can apply to the AIC. It's a 2-page proposal. If you're accepted, you come. We pay for your stay in our hotel on site. We give you nice meals, a pub with booze in the evening. But basically you'll feel like you're on a synchrotron beam line. You'll work 18-hour days along with us for your 1 to 2 week window to get as much data as you like. And everybody goes away with 10 terabytes of data and a big smile on their face, and a week later they come back frowning saying, we don't know how to analyze 10 terabytes of data. And that's a big problem with these microscopes. But everybody has fun and learns a lot. And that creates, hopefully, a market or an interest in the microscope. So those who have either the technical chops themselves or can collaborate with engineers and physicists who have the capability, we thoroughly document all of our microscopes, and we create a Dropbox folder where you can get all of the details from down to the screws and where to order them, and all the control code and everything else. And we put on a workshop where we tore apart a lattice light sheet microscope, put it back together again, filmed the whole thing, put that whole video, also 5 days of video in the Dropbox folder, trying to make it as easy as possible for people to replicate the technology for biologists. And then the long-term answer is commercialization. And AIC, a lot of that is to make it so that there's enough interest in the technology that the companies are willing to invest the R&D resources necessary to make a commercial product, and to make sure that when the time comes that that product comes to market, that the funding agencies know about this so that people can put in grant proposals and have the money to be able to buy the microscopes that the companies sell. So that's the whole plan of this sort of tech transfer. And so with that, I'd like to conclude and thank, in my case, one of the secret weapons of Janelia is the visitor program, is that we're able to have many, many visitors. We've had probably 80 different labs come visit my lab personally to do all the, this is a tiny, tiny fraction of all the stuff that we've done with these microscopes. And the other secret weapon is being at Janelia itself, to have an environment that, like Hugh Kelly had, and like Roop had, and like Tim Sands had, and like I had, where you could focus 100% of your time on your work without distraction. And that's so meaningful, to not have to teach and not have to write grants and not have to do all this stuff. It is so powerful and so liberating to do that. And the ability to work with small groups. This is my group when it was 5. I'm at 4 again. I've averaged 3.5. Everything you've seen, and this is, 5% of everything there is the output of, on average, about 4 people over 10 years, okay? I really feel that having a much smaller group than all my competitors gives me an unfair competitive advantage compared to them. And so, I think a lot of this philosophy came from Bell. And so I'm really grateful to have been part of 2 great institutions who believe in that. Thank you.
Well, in simple words, wow. It's a story, a very inspirational story. It's a story of hard work, tenacity, insights, and you can see what that can do for us. We can now come up, I think finally we have a tool which will allow us to understand life at its fundamental level. So with that, I will ask the audience if they have any questions. I'm sure you'll be able to take any questions.
Sure. Yeah.
So let's see.
Get a microphone and run around.
Yeah.
She's going to take the microphone.
Wherever I want. Oh, there it's here. Yeah, it's here. It's in the back. Or get shoved underneath.
Oh,
Yeah. Go ahead.
Hi, great talk.
Is it on here?
Hello? Okay, yeah. Is it possible to combine this with Raman spectroscopy to get resolution of metabolism?
Yeah, a lot of people ask that. It is possible. The question is how much damage will it incur, right? Because generally the intensities required for significant Raman signal are pretty high, right? So you have to find the right problem that could accept that kind of intensity. Now, one thing that we're doing, that's in the live cell. Now, if it were fixed, it's a different story, right? Then you could do other things. Now, one of the projects I didn't get a chance to talk about is Harold, my buddy Harold and I are teaming up again on a crazy project to, remember I said fixation artifacts are a problem. The EM people get around this by slamming their cells in liquid nitrogen very quickly so that you vitreously freeze them in place with amorphous ice instead of water crystals. And we basically have a cryo super resolution microscope with palm and SIM capability, with the capability to correlate a VM. And our goal is to do this again down at 4 degrees Kelvin. So that what happens there is several things. First off, you freeze out any damage mechanisms or bleaching. So that also brings into play Raman and other nonlinear optic technologies to explore near absolute zero. And also it makes the fluorescent line widths extremely narrow so that potentially you could multiplex and see many, many more proteins at the same time. In my opinion, one of the remaining there's two holy grails, Raman relates to one, is that in microscopy, is that I have a love-hate relationship with fluorescence, and having that fluorescent tag is a nasty little bowling ball, and it's a pain in the butt to put there. Raman has intrinsic signals, so it's label-free. The problem is there's been great work on label-free optical imaging, but none of it with really good protein-specific contrast. That may become in play at low temperature, so that would be great for label-free side. The other holy grail is that any process inside of the cell involves dozens or hundreds of proteins working in concert. And so you would like to see those dozens or hundreds at the same time. And with the narrow line widths that we might get cold, that might be possible.
Any other question? Well, let's thank our speaker one more time. And before we let you go, we have a small gift of appreciation
Okay.
for our speaker. So, if I may,
Wow.
please.
Okay, good. Thank you.
Thank you
Thank
very
you
much.
Yeah.
And lastly, I would like to take this opportunity to thank Eleanor, our communication group, the ICTA staff for pulling this event together. So thank you very much, all of you who are here, and those who are not even here. So give them a hand.